Welcome to The Explainer. Okay, let's dive right into this, because today we are tackling literally the ultimate cosmic mystery. For nearly a century, scientists have been trying to figure out what actually makes up our universe, and honestly, the answer is going to completely change the way you look up at the night sky.
You know, the composition of our cosmos illustrates exactly why this is such a massive, mind-bending mystery. Think about it. Everything we can see, I mean everything, from the billions of stars and galaxies out there, all the way down to the shoes on your feet. That makes up just a tiny 5% sliver of the universe. That's our normal, visible matter. The rest? It's made up of two immense, completely invisible components. Dark matter at 27% and dark energy at 68%. Today we're zeroing in on that 27% because without it, well, the universe as we know it simply wouldn't exist.
Section 1. The universe's invisible glue. We can kind of think of this next part as a cosmic crime scene where the math just didn't add up, and scientists were forced to realize that most of the universe's mass had essentially gone missing.
Tracing this cosmic timeline back to 1933, Swiss-born astronomer Fritz Zwicky was studying the Gamma cluster of galaxies. And he noticed this incredible anomaly. The galaxies were moving entirely too fast for the amount of visible matter inside them. Basically, they should have been escaping the cluster, just flying apart into space, but they weren't. Fast forward to the 1970s, and American astronomer Vera Rubin found the exact same missing matter problem, but this time in spiral galaxies. The stars on the outer edges were moving way too fast. Without a massive amount of unseen matter holding them in place, those galaxies would literally tear themselves apart.
So the crucial takeaway here is that there absolutely had to be an unseen force acting as a profound gravitational glue, literally holding these massive galaxies together. When Zwicky first noted this bizarre discrepancy back in the 30s, he dubbed this mysterious material Dunkle Materie, which is German for dark matter. It was the birth of an idea that spread like wildfire and is now widely accepted by the scientific community as the absolute foundation of galactic structure.
So let's clearly define our invisible suspect. Dark matter is this mysterious mass that interacts with ordinary matter through gravity. It absolutely takes up space, and it definitely has mass. But here's the kicker. It doesn't seem to interact at all with the electromagnetic spectrum. It completely ignores visible light, infrared, gamma rays, you name it. It does not absorb, reflect, or emit light whatsoever.
Section 2. Catching the invisible. Now, this begs a massive, completely valid rhetorical question. How on earth do you discover something you can't even see? Well, the answer lies in a sort of cosmic magnifying glass called gravitational lensing. Because dark matter has mass, its intense gravity can actually bend the fabric of space-time itself. When light from distant background galaxies travels past a massive cluster filled with dark matter, that light gets bent, creating these warped, streaky, and magnified images. So, by measuring those specific distortions, astronomers can literally map out the distribution of the underlying invisible dark matter clouds. It's like seeing the invisible wind by watching how it bends the trees.
And that brings us to the real smoking gun. In 2006, scientists observed the Bullet Cluster. This is about 3.8 billion light-years away. Two immense galaxy clusters, which, remember, are massive groups of galaxies held tightly together by this very dark matter, slammed into each other in an extremely energetic collision. When they crashed, the hot X-ray emitting gas, which is the normal matter, interacted and slowed down. But gravitational lensing revealed that the vast majority of the mass, the dark matter, kept right on going. It completely separated from the normal matter. It's really one of the clearest, most direct examples we have showing dark matter as a distinct physical entity. Now, this leads us to a fascinating question. Does dark matter have a temperature? Well, because dark matter has mass, the laws of physics dictate that it absolutely must have a temperature. And figuring this out tells us exactly how it behaves. Scientists actually ran massive simulations to model the universe under two totally different conditions: cold dark matter versus hot dark matter. Hot dark matter would be made of extremely fast-moving particles. But in simulations, those fast particles prevented cosmic structures from sticking together, which simply doesn't match the reality of the universe we actually live in. Cold dark matter, on the other hand, is made up of slow-moving particles. These simulations perfectly matched our reality, allowing early structures and galaxies to form, group up, and definitively stick together. So scientists currently agree, for sure, dark matter is cold.
Section 3. Profiling the prime suspects. So, That narrows things down a bit. But what exactly are these cold, slow-moving particles? Let's take a look at the current lineup of hypothetical candidates that scientists are actively hunting for right now.
We really have three leading suspects. First up, we have WIMPs, or weakly interacting massive particles. These guys are big, heavy, and slow. They pass right through normal matter, but if two WIMPs interact, they might annihilate each other and produce highly energetic gamma rays. Next, we have axions. These are the complete opposite: tiny, low mass, and low energy. They were actually originally theorized to solve some really complex mathematical quirks from the early universe. Finally, we have primordial black holes. Now, these aren't your typical dead stars. These formed right after the birth of the universe. They could be incredibly dense, ranging from the size of a single atom all the way to supermassive giants.
And make no mistake, the hunt is absolutely on. NASA is actively searching for all these suspects using some of our most advanced space telescopes. You've got the Fermi Gamma Ray Space Telescope looking for WIMP annihilations and black hole evaporation. Meanwhile, the Chandra X-ray Observatory and NuSTAR are out there scanning the cosmos for signs of axions. While the true culprit remains unconfirmed, we definitely have our best detectives actively on the case.
Section 4. Dark matter versus dark energy. Before we wrap up this explainer, we really need to address a major point of confusion. Because they both have the word dark in the name, they get mixed up constantly. But they do completely different things in our universe.
The crucial point to remember is this. Think of dark matter as the invisible glue. It's concentrated in and around galaxies, and its gravity pulls things together, allowing structures to form and holding those galaxies securely in place. Dark energy, however, is the accelerator. It is spread dynamically throughout the entire universe, and it is actively pushing things apart, causing the universe to expand at an accelerating rate. Simply put, dark matter pulls it together, dark energy pushes it apart.
When you combine the invisible glue holding galaxies together with the accelerator pushing the universe apart, you get this massive, mind-boggling number, 95%. Dark matter and dark energy together account for 95% of absolutely everything in the universe.
Which leaves us with this final, profound thought to end on. If 95% of our universe is dark and completely invisible to our eyes, what else are we missing? Every star, every planet, every living thing we have ever known fits into a tiny 5% slice of reality. The rest is out there, just waiting to be discovered. Thanks for joining me on this explainer, and keep looking up.